Okay. Couple of other announcements I wanted to make. There we go. I was wondering if it was going to open up. There we go. Yeah. And it doesn't look like it got kicked too wildly as people were leaving the last class. Maybe that's okay. Okay. All right, we will get to that in just a second. Go through the last few things. I think I've given everybody here the last test, or have I?
Test 3?
Yeah. Yeah, you just turned it in. Have I given it to you yet? You? Let me see. It's the one on, okay, I'm sorry. I was thinking another class. Okay. It is the third test, but it says test 2 on it. Okay. It starts off let f of x equal 2x squared plus y squared minus 4xy. No. Okay. All right. Well, I was going to give it to you at the end of the period. I can go and give it to you now. But a couple of people had come out earlier. This is the one you did, right? Yes. Okay. This will be your last test. At the end of class today, I'll let you know how many of those are for credit and how many are bonus, okay? Because I don't know if we'll get them all covered or not. I think we might, but we'll see. Okay, there's that. Okay, they are due by next Thursday. If you can get them to me later today, I'll be here till probably 5. I doubt it, but I will be here. Tomorrow I'll be here 7:45 until close to 8 o'clock in the evening. Friday I'll be on the Birmingham campus in the morning, 7:45 to 11:45. And then next week I'll be here on this campus Mondays and Wednesdays, 7:45 until sometime between 2 and 4:30 or 5 in the afternoon, and Tuesday and Thursday from 7:45 in the morning until 8 in the evening, but not on Friday. So I have to have all your work in. Now your research papers are due in today, right? Okay, you went out and got Matt, good. Okay, I sent him out to get you. Okay. What's that? Okay. Yeah. And I give you a copy of that yet? I haven't. I think so. Okay, we'll talk about at the end of the.
Oh, test 2 again.
Yeah, it's the second test too. Okay. All right. But I was saying these are due in no later than the end of business on Thursday, which for me is usually 7:45 or 8 o'clock at night on Thursday. Please don't bring it up here on Friday. I will not see it. I will not be on campus on Friday. We'll be heading to New Orleans on Friday. I've got a meeting down there. So I have to have them then because grades are due in by noon on Monday. So if I don't have it by Thursday evening, I'm not going to see it again until Monday morning, whether I have a chance to get it graded and all the things done by noon, I don't know. So try to get it in. The sooner the better, but get them in. Research papers are due today. I'll be here till probably at least 5:15 today, maybe even later, but probably at least 5:15 today.
At least till 2.
Well, definitely till 2. But I've got one test to type up, another addendum to a test to do, and then I've got grading out the years to do. So I'll definitely be here till at least 5:15. Okay, and maybe later. All right, last thing, one of the last things, student course evaluations. Okay, do all of you know how to access those? Do you?
I got an email on it
Today they did again? Okay. Do you get your Lawson email?
I use my Crimson email.
What's that?
My Crimson email.
Right. Well, they probably won't send it
Can
there.
I access it on Blackboard? Or?
Yes, you can. Well, not Blackboard, or can you on Blackboard? I know you can through the website. Second? Yeah, the Lawson State homepage on the website. You can access it that way. I'm trying to think, okay. On the Lawson State webpage, it's mostly in blue. But there's one big gold tab, not really big, but it's called Quick Links up in the upper right. If you click on that, it's pretty much alphabetical, but not completely. Scroll down until you see surveys, I think it's called. It could be evaluations, but I think it's surveys. But scroll down till you see that. If it says student, look around. You know how to go through a website. See if you can find those. And the name of the program is called Smart Eval. SMARTEVAL, all written as one word. If you see that, click on that. And it'll have directions for what you use as you'll need probably your ID number, don't you? And you know what your Lawson ID is?
Yeah.
Okay. And you'll need your birthday is the other part. So with that, you'll get it. Now, how do they do birthday? Year, month, day?
6 digits.
Month, year, day? What's that? Yeah, four digit year. It's an 8-digit number. I just couldn't remember the order.
I can never remember the order of day and month.
Of course. So it doesn't matter. Okay. Unless you were born in that year too. No, never mind. Which would be difficult. Right. Yeah. All right. And here is Tony, right? Goodness, that's right. That's right. I think I've got it.
And it's somebody.
Wow. And they keep coming. Oh, no. Okay. Yes, sir. What's that? Okay. Not up here. I have down in my office. So it's fine. Okay. All right. Thanks. I'm sorry. Okay.
See you next week.
Okay. All right. 3, 4, 5, 6. Okay, I think I got everybody marked now. Okay, so please do the student course evaluations before the end of the term. Don't wait until they close them out. They'll be open at least through finals and maybe a little bit after that. But don't forget. I know when I was an undergraduate, as soon as that last final was taken, the mind turned off. Okay, thank you so much. So,
You don't need it anymore.
yeah. Oh, yeah. I was going to give them out at the end of the period, but this will do too. Okay, good deal. And at the end of the class, I'll tell you which ones you can do and which ones you don't need to do. Or a bonus, I'll put it that way. All right, any questions before we get going today? All right. Okay. We have seen that the rate of change of a function of several variables depends on which direction you're heading, right? So it matters, okay? Depends on your choice of direction. Since directions are indicated by vectors, it is natural to use a vector to describe the derivative of f in a specialized direction, specific direction. To do this, we introduce the concept of a gradient, okay? Now, this doesn't do a lot to explain a gradient, it just defines the gradient, okay? This symbol is often called a del, not a delta. A delta is the point up. This is called the del with the point down. I don't know of any other place it's used except this. It's not a member of the Greek alphabet. It's upside down delta, capital delta. But it's called the del.
I think it's just a marketing scheme.
Yeah, okay. And it indicates gradient. So quite often it's read either del F or gradient of F. There's hardly any way to bold something that's not a symbol. It's just a symbol, that's all it is. Think of that as bolded. It indicates this is a vector. This is a vector. It goes in vector brackets. The gradient is a vector. Its components are the partial derivative of the function at that point. Okay? Now, if no point's given, then it's given in terms of x, y, z's, or whatever. So the gradient of f at point P, if point P is the gradient of a function f of x, y at some specific point P of AB, where x equal A, y is equal to B. At that particular point, the gradient is the vector. It is a vector. When I do this, I put a vector symbol over it. The gradient of f at P is the partial of f with respect to x. That's the x component of the vector evaluated at AB, comma, the y component. In 3 dimensions, it's f sub x ABC, f sub y ABC, f sub z ABC. The partial of f with respect to the first, second, third variables evaluated at this point. Now, if you're not given a point, then you do it in terms of x, y, and z. But it's the partial of f, partial of y, partial of z. Those are the 3 components of the vector. Okay. Now, by the way, some of you haven't chosen the paper type yet and get it done by the end of the day. There was a Scotch physicist named P.G. Tait, T-A-I-T, who called the symbol a nobla. Okay, fine. Great physicist James Clerk Maxwell. It looks like it's Clerk, but it's pronounced Clark. He was Scottish. Was reluctant to adopt this term and would refer to the gradient as simply the slope. He wrote jokingly to his friend Tait, who was also Scottish, still harping on that neighborhood, or something like that. Anyway, that's pretty cute, I guess. It's meaningless. I don't know why they put it there. But anyway, that is what it is. Now, I think this is used in example 1. It's a pretty lousy figure. Let me see if zooming in will make it any better. I kind of doubt it, but it might make it a little bit. Okay? Yeah, I think so. Let f of x be, f of xy be x squared plus y squared. Okay. Now you might think of that as just being the circle of radius 1. That would be one way of thinking of it, but this could be defined anywhere in the xy plane. So it doesn't have to be that. It's just anywhere there. Calculate the gradient del f and draw several gradient vectors and compute del f sub p at p 1, 1. They've done more than, well, they haven't even done that here. But let's do it, okay? Calculate, let's do first what they said. Of course, I have to shrink it to right. Okay, yeah. Here's your f of xy. What is grad, that's sometimes called grad 2, by the way, grad f at xy? The gradient of f of xy, or del f at xy. What would that be? Number 1, it is a vector. So in vector terminology, what would be its components? A little louder. Say that again? No, it's f sub x. First, the partial of f with respect to x would be 2x, comma 2y. Those are the components of the gradient vector. Exactly. Now, when x equals 0, y is equal to 0, you got the 0 vector, not going anywhere. Not one of my favorites. But x equals, say, 0, 1, this would be at 0 on x minus 2 on y. They didn't draw this from here, but that would be it. It would be a vector downward in the minus 2 direction. So everywhere it's pointing outward. Okay? Everywhere. Negatives, whatever. Now, said draw several gradient vectors. They picked a few. Here's the point 1, negative 1/2. At that point, the gradient vector would be components, or 2, negative 1. 2, negative 1. There's a gradient vector at that point, pointing away from the origin. At 1, 1, that is one that they gave. That would be 2, 2 would be the gradient vector. Again, pointing exactly away from the origin. Over here at negative 1/2, 1/2, that would be negative 1, 1. And there's your vector here. Notice the closer to the origin you are, the shorter the vector is, the farther away you are, of course, the bigger the vector is. Okay? So yeah, that's several of them. Including the point 1, 1. Okay? No, they didn't show 1, 1, did they? What would it be at 1, 1? So del F at 1, 1 would be 2, 2. So that would be this one. Well, there it is. Why didn't I see that? There it is right there. I kept thinking I had seen it. Okay, so there's that one. Any questions on that? Pretty straightforward, pretty simple. Let's do it in 3 vectors. Okay, don't think they have a graph of this one, so we'll just clear all this off here. We'll do this up here. Calculate del F at the values 3, negative 2, 4, where F of x, y, z, I can't write, is equal to z, I say z and write e, z e to the 2x plus 2y. Okay? What we want is the partial. Is 3y. I can't read either. Okay? We could do better than that. Okay. Now, you can do your gradients separately, or you can do them as you go. How you want to do it. Say again? Separately? Okay, let's first calculate F sub x. What would that be? Two z e to the 2x plus 3y. Perfect. F sub y. You said 3z? Okay. E to the 2x plus 3y. Excellent. F sub z. E to the 2x plus 3y. Do you see why that's true, everybody? All right? So we want to calculate del F at these points, at that one point. So del F at this point is equal to F sub x is your I component. So let's see what that would be. 2 times, help me. Yeah, but x is, okay, 2 is that 2 right there. Okay, x, or z is 4. E to the e to the, okay, you already did it. 2 times 3 is 6, plus 3 times negative 2 is minus 6, so that would just be e to the 0, which is 1. Okay? So I could have written that. In fact, I will write that. 8. Okay? 8 is the x component. What's your y component? 3 times 4 is 12. And then your exponent is still 0. So it's e to the 0, which is 1.
And then the next was
1. You got it. There is your del F at that point. Okay? We don't have a graph of that. Thank you very much. I don't have to draw it anyway. But that would be the gradient F at that point. It's increasing 8 units per every unit it goes over the x direction, 12 units for every in the y direction, and just going up 1 in z. So it's, I did them up, I shouldn't be going up. Anyway, that's your gradient there. See if they got it? Yeah, 8, 12, 1, good for them. And that is our brackets, angle bracket. It's a vector, not a point. Okay. Now, next slide, the following theorem lists some useful properties of the gradient. The proofs are left for the exercises. Isn't that great? 64 to 66. So if you're wanting to see these proved, go home and do them. Okay. All right, here we go. So we have two functions. Gradients are taken of functions, if you hadn't noticed that. Scalar functions, when you take a gradient of it, you get a vector. Okay. F of x, y, z and g of x, y, z are differentiable, and c is a constant. Okay? Then, the grad of a sum, the gradient of a sum, is the sum of the gradients. Okay? About what we would expect, I hope. The gradient of a, Victor's here. Don't leave before you pick up your test. The gradient of a constant times a function, either one of those functions, would be the constant times the gradient. In other words, the constant can come out in front of the gradient. Because you're taking partials and the constant comes out in front of each of the partials. Now, the product rule for gradients, okay, probably about what, hopefully about what you would expect. The gradient of a product of two functions, this is the gradient of a sum, the gradient of a scalar multiple, the gradient of a product of two functions, be the first times the gradient of the second plus the second times the gradient of the first, just like your product rule in functions, in derivatives of functions. Okay? And it doesn't matter which one you put first. You can put the gradient of g first and times f, or you can put f, gradient of f times g, and then add, addition and multiplication are commutative. You can put them in any order. The chain rule for gradients. If capital F of t is a differentiable function of one variable, then if you have the gradient of the function, this function, and that t is a function of x, y, and z, so you do the gradient of the outer function, okay, and only that's a derivative of the outer function, because it's only got one variable, t. Derivative of the outer times the gradient of the inner. Okay? Derivative of the outer times the gradient of the inner. Chain rule for gradients. Now, I can almost ask this, or picture the student saying, student as opposed to pupil, saying, what if you had a multivariable function here, like the little f, of other single variable functions there. It gets a little messier, so don't worry about that yet. Let's deal with this one first. Okay? That gets into I can't think what you call them, but parameterization, that kind of stuff. I doubt if we'll get a chance to get that far. Okay, but we'll live with these to begin with. This followed by, I think, the next example. And I think, no, we don't have a figure for that one either. This figure doesn't apply there. So let's go back to here and do example 3. Find the gradient of this, gradient of g of x, y, z. If that is x squared plus y squared plus z squared raised to the 8th power. So g is actually, in a sense, a composite function. Okay? So what would you say that gradient would be? How would you do that? Okay? You could. You want to take the partial first, that's fine. What would that be? Okay. Just because I like to have it out in front, let's do the outside one first. 8 times x squared plus y squared plus z squared to the 7th times, second, 2x, not plus, 2z. That's your gradient. So that's a vector. Now you could take out the 2 and make it 16 x squared plus y squared plus z squared to the 7th power. That's all a scalar quantity for whatever values x, y, and z are, multiplied by the vector x, y, z. It's a variable coefficient of the vector. Okay. See how they express it? I think that's how they did. And I kind of like having the scalar part in front. It's like a coefficient in front of your vector. Okay? That's why I'm sort of resisting taking the gradient first, because then you would have that written in front, and then you'd have the other. It doesn't matter. You can do it, but you just somehow feels a little better to me to have the coefficient part in front of the vector afterwards. Okay. Not that it matters. Okay. Now, this is what we're going toward next. Okay? It's not gradients anymore. That covered gradients. This section is gradient and directional derivatives. So now we're going to head toward a directional derivative, and gradients will come back into the picture then in just a minute. So, what they're calling this is the chain rule for paths. Okay. I'll blow this up. All right. Parametric equations. The C of t is sometimes called a path, even though they bolded it as if it's a vector. They're not calling it a vector, they're calling it a path. Okay? Now, this happens to be, they don't show you what it is, I'll make a real good guess at it. It's something like cosine t, sine t, t, or something like that, because it appears to be a helix, okay, kind of a slinky spring, okay, looks like the cross-sectional area looking down on it is a circle. May not be. It could be a constant in front of the x, the cosines of the sine if it's bigger than 1 radius or smaller than 1 radius, okay? Could be a coefficient there. You could have multiples on your t, but we don't know. It doesn't matter, okay? But this is your curve. They put a bold as if it's a vector, but that represents the curve. Now, the derivative of that, the tangent vector of this curve, is in the direction of its curvature. It's tangential to the curve, but also going in the same direction of it. That's what we're looking for, C prime of t. Now, this is a vector. C of t, the green, is not a vector, it's a curve. That's y of t, okay? But they bold it, nevertheless. But the derivative of that curve is a tangent vector, okay? And it's to this path. I'm sorry, I call it a curve. It's a path. The book makes a distinction there, okay? Now, that's where we're gunning here, okay? Now, one thing they left off, oh no, they didn't. No. Yeah. Boy, they've done it here. This is from the old text. In the new text, they're indicating this is your R of t, okay? Again, this is the first time I've taught this class from this new edition, so this sort of snuck up on me here. The first application of a gradient is a chain rule for paths. Chapter 13, way back there, we represented a path in R3 as a vectored value function, R of t, and that's what your book has put this. Now, to go to write it, I have to shrink it. To write on it, I have to shrink it. Well, I think it's already got the fit. No. Okay. What they wrote here is R of t as a vector is equal to x of t, y of t, z of t. Okay? Now, technically, what the R of t is from the origin to that. That is really what the R of t is. And at different t's, the arrow on the R function traces the path that's the C of t. Okay? That's the difference between them. They look just alike. But if you talk about the curve, in other words, the trace of the point as you let t increase, that's the green curve. The R of t is the individual vector pointing at any time t to that place on the trace. Okay? So this slide shows the curve. This one acts as if that curve is the displacement vector. The displacement vector, that's where the point of the displacement vector would be. All right. Minor points, but it's rather bizarre. Okay? Now, when there's no harm in doing so, we will sometimes think of R of t as the path of the endpoints. That's what I was just trying to say, of the vectors, rather than the path of the vectors themselves. Okay? So it's the path of the end, which the book, the old edition, called the path C of t. Okay? And this one does too. The path C of t is that path that was taken by the point of the R of t vectors. So the R of t is a vector, C of t, even though they're both bolded, is actually just the path. The trace of the, I don't want to use that term either, that means something else. Now, okay. So, thus we might write R of t equal parentheses x of t, y of t, z of t, rather than R of t as the angle bracket x of t, y of t. really, if you're doing the parentheses, put C. If you're doing the R of t, put bracket. Because that's actually a vector. Now, by definition then, R prime of t, which is also going to be a vector, will be x prime of t, y prime of t, z prime of t, whereas all the primes are in respect to t. Okay? That's also a vector. Now that's going to be this c prime of t. Those are identical. Okay? This and that are both vectors, and you can call it either one of them. Rather strange, but true. Also, that r prime of t is tangent to, and it's the velocity vector that is tangent to the path and points in the direction of motion. We use similar notations for all paths in R2, R3, wherever. Now, the chain rule for paths is what they're talking about here. Deals with composite functions of the type f of r of t. Okay? F of r of t. Okay. Now, this was the reverse of what I was saying before. I said we'll get to it. We got to it sooner than I thought we were. Okay? And see, before what we were doing was capital F of t, but little t was a function of three variables. So it was the derivative of F, that was just the chain rule for the function, then the gradient of the components of the function. Okay? Now we're doing the function which has a vector, is a vector function. It's a function of the vector quantity. So your vector components are inside the function. They're the thing you're operating on. Okay. Think of this sort of like a potential function. Potential function is operating on a vector, but giving you a scalar answer. That's what this is indicating. It's a function quantity of a vector component. Okay. Now, what is the idea behind this composite function of this type? For example, suppose that T of xy, capital T of xy, is the temperature at any location xy. Let's see. This is something we've sort of already talked about, so I'm not going to go into that. Here's what we got. Now the C here doesn't stand for Chloe, but it sort of looks like it does. Okay. Here Chloe is riding a bicycle across the U.S. Okay. Crazy person. Okay, no. Chloe's temperature changes at a rate of del T at C of T times C prime of T. Okay, now what does that mean? The gradient function here, okay, start with the function, T of xy. At any place xy in the U.S., continental U.S., let's say, any value x, y, there's some temperature at every one of those places, right? That's the external temperature there. Now, del of that temperature, and it depends on both your east-west location and your north-south location, the temperature changes. Usually as you go further off, you would think the temperature would decrease. If you go further east, it may decrease or increase, just depends on what your weather pattern is, okay? So the del T would be a vector quantity that is indicating, and that would be these blue lines, that's how the temperature is changing. It's increasing as you go, well, it's hard to say looking at this, but the pathway, the green is your C of T, okay, that's your path. C prime of T is tangent to that path. Del T gradient of T. T is the temperature at any point, scalar quantity. You got it. Thank you so much. Okay. I'm never finished grading. Okay. It's how the temperature is changing as you're going both east-west and north-south. Okay. That's how the temperature is changing. And your C prime of T is your speed along that direction. So her temperature changes at the rate of how the temperature itself is changing. That's a function, a vector function, dotted with, that's a dot product here, with another vector, C prime of T. Now remember, C wasn't a vector, but C prime was. And that's your path there. So it's how the temperature is changing as you're changing X and Y, dotted with how your course is changing, how your path is changing as you go increase in time. Okay? This gives you a change in the X and the Y direction, and this gives you how the temperature is changing with those changes in the XY direction. So the dot product of those two gives you how her temperature is changing as she's changing course and changing temperature because of the change of course. So that yields a dot product. Okay? At least it's fun to look at. I'm not sure it's all that clear why that's true. And it's not Chloe anymore, now it's Alexis. I don't know why they changed that, but they did. And the new edition is Alexa. Okay. So here's the chain rule for paths. Theorem 2. Okay. If f is some scalar function and c of t is some path along that scalar function, it's going to be interesting. Okay. In your book, new edition, I'm going to have to shrink it to write it, this is now r of t. To me, this makes so much more sense. I used to really struggle explaining to students the C of t is a path, but it's not a vector, even though it's bold like a vector. They cut that out and go back to r of t. Thank you very much. Okay. So everywhere you see a C, a C here, it becomes an R, which is actually a vector, because r prime and c prime are the same, so why not call it r? Okay, so if f is a scalar function, r of t is a vector function, they're both differentiable functions, then the derivative with respect to t, remember f is a scalar function which could have 2, 3, 15 components, whatever it has, okay? But r is just a single value function. It's a vector function, but of a single variable. It has components that are different variables, but it's a single independent variable. Then what is that? Well, a derivative of a scalar function of the vector quantity is the gradient, which becomes a vector. And by the way, that C also becomes R. I know it's hard to read. And those are bold R's. I didn't put the arrow over that. The gradient of F at R of T, dot product with R prime of T. So it looks like another chain rule. And it is. Only this d by dt becomes a del because R has more than one component. Either 2, 3, or 15, or whatever number of components. And if you're taking a derivative of a multi-component scalar function, that gives you a gradient. Okay? And then dot that with the r prime of t. That is just the first derivative. Derivative, not gradient, because it was already a vector, and it only has a single value, so it's dr dt. Explicitly, in the case of two variables, where C of t, or R of t and now that's a vector symbology, okay? Well, they do it three. Okay. In the old thing, it showed 2. In the new one, it shows 3. Okay? So if R of t is x of t, y of t, z of t, or as many t's as you got out there, then the derivative of this function, which is only a function ultimately of the independent variable t, but the intermediate variables do have meaning, f of R of t, and here, let's change it again. And I really appreciate the R changing that. It drove me nuts before, trying to explain to students. Just call it R of t. The derivative with respect to t of f of R of t, composite function here, but it's a scalar function acting on a vector function. The ultimate independent variable is t, but the vector function is going to have the intermediate variables x, y, or x, y, z, or whatever. Okay? Then it would be the gradient of f, which is partial of f with respect to x, partial of f with respect to y, partial of f with respect to z, as many as you have there, that vector dotted with the derivative of R of t with respect to t, which would be x prime of t, y prime of t, z prime of t, and so on. Well, what is that? The dot product of these is the first by first, second by second, and it's a scalar, not a vector. Okay? So this is because the dot product produces a scalar value. The partial of f with respect to x, dx, dt. There you have it. Plus the partial of y, f with respect to y, dy, dt. Plus the partial of f with respect to z, dz, dt. And it just keeps on going that way. Now, what does it ultimately look like? It looks like these could sort of think of canceling out. They don't, but it would be derivative. The change of f with change of t. That's what you're looking for to begin with. Change of f with respect to t. You've just got this intermediate thing in there, which does. Now, I don't know if this is helpful or not, but when you're doing the chain rule, as we did before in Theorem 1, for gradients, if you have del operating on a function, and the function has components in it, since del is operating on that, that's going to come out being a vector. But if you're taking the derivative of a scalar function of a variable, even though the intermediate function is actually operating on a vector, this is a derivative of a scalar function. It's going to be a scalar. Sure enough, that is a scalar value. Okay, so Theorem 1 gave you vector because you were doing a del of composite of two functions. Now you're doing derivative of a composite function, and that's going to give you a scalar, not a vector, because of the dot product there. Okay. I don't know if that's helpful or not. To me, it helps me remember which way to go on it. Okay. I think we changed everything we can there. Now, they do have a little proof there, and we just don't have enough time to go through proofs. Read through that, see if you understand it. If you don't, come see me sometime during office hours. We'll go through that. Now, I think we're ready for example 4. Yeah, here it is. Temperature at location xy is T of xy okay. They don't have that anywhere on the thing, so let me write it. So I'm not going to blow this one up. T of xy, temperature function of location, two-dimensional. That's equal to 20 plus 10 e to the minus 0.3 times x squared plus y squared. And this is measured in degrees Celsius. That's a function based on xy position, okay? But it's a temperature, okay? It gives you a temperature. It's a scalar function based on positions on a two-dimensional plot, okay? So, a bug carries, this really makes a lot of sense, a tiny thermometer along a path r of t, and this, what they're calling c of t is now r of t, path r of t, which is cosine. This is a great improvement, even though the slides are not up to date. I lost it. There it is. Cosine t minus 2, first component, sine 2t, second component, where t is measured in seconds. Okay? Shown in this figure. There's the little bug crawling along the green path. Now, just based on what I can see here, it obviously is moving in this direction. Why do I say obvious? Because you see of 0.6, x is 0.6, is in that direction. So I know it must be heading that way. All right. Now, how fast is the temperature changing at t equal 0.6? That's where that comes from. How fast is the temperature changing? How fast is dt? Now this is capital T is temperature per time t. Okay? At time t is equal to 0.6 of a second. Okay. All good. Jonathan's here. If I'm not mistaken here, every Y chromosome has shown up today. It's the X we're missing. Okay. But she's been working on it. So, all right. Those who've come in recently, don't leave without picking up your last test, which is your final exam. I guess I ought to say it again since everybody's here. Okay. You'll pick up this last test. It's test 3, even though it says on the top test 2. I didn't get that changed. It's 2, the sequel. Okay. But anyway, it's just covering what we're doing in chapter 14. I had to make out the test before we got through, so I don't know if all the questions will be on it. I'll let you know before the end of the period, right at the end, if there are any optional questions at the end. But it's covering chapter 14. Now, you pick it up today, you can turn it in to me later today if you finish. Not likely, but possible. Tomorrow I'll be on campus all day until about 8 o'clock in the evening. Friday I'll be on the Birmingham campus in the morning anyway, 7:45 to around 11:45 or noon or so. Probably be there later, but at least that long. Next week, Monday through Thursday, I'm on this campus, Mondays and Wednesdays till about, let's just say, anywhere from 2 to 5, maybe later. Definitely till 2, but probably later than that. And Tuesdays and Thursdays, I'll be here until 8 o'clock in the evening again. So Monday through Thursday of next week, sometime before Thursday, get me the test back. Okay, now you should have turned in the paper today. You have till the end of the day to get the papers to me, research paper. After today, you start losing points on the paper. So get them to me today and you get the full score. Okay. The previous test, I would like to have those today because I want to return those to everybody, but I don't have all those in yet. So I'll return it to the people who have turned them in, but please don't share them with people you're not sure turned one in, because you might be giving correct answers to someone who is going to get a better score than you then, so you don't want that, of course. Right? Okay. So get those to me today, preferably. Now, I do need all the papers by Thursday of next week. Why? Because I'm out of town on Friday of next week. So if you turn it in on Friday, I won't get it until Monday. And whether I'll have time to get it graded and the grades in by noon on Monday, doubtful. So try to get it to me sometime this week or next week. Probably going to be next week, but I'll accept them this week if possible. Research papers I want today or as soon as you can. You might be losing points after today, but get them to me as soon as you can. All right. So we're back to the bug. He's not on the bicycle, I don't guess, but he's traveling along this curve. Okay? Now, notice the temperature function is everywhere on the screen. Everywhere. Okay? Every point has a value, x, y, and therefore it has a temperature function of x, y. The path this bug is traveling is this path right here. And just keeps going this way. Okay? So he's just traveling there. He's not going to ever get to this temperature here, or this one over here, or this one right here. He's going to be on that path. But on the path, there's a temperature at every point there. What's his temperature at t equal 0.6? That's the question. Well, you got to find out where he's going to be at 0.6, how fast he's going at 0.6, and determine what his change of temperature is. Okay. Because the question is not what his temperature is then, it's how fast his temperature is changing then, which is this thing. d by dt of the temperature. How is the temperature changing with regard to time? Okay. At this time here, 0.6 of a second. Okay. How would you do this? Okay. Since I heard a rousing response to that. Okay. Say again? Okay. Actually, do the derivatives first, then plug in. Okay. But good try there. Okay. So basically, let's see, let me get the best way. No, actually, I take that back. You're right. All they want is to plug in. Well, wait. Even though they say that, okay, okay, you're kind of right. And what I was saying was also has meaning here too, but here's what you have to do. The R of t, this thing, locates the bug for you. Where is the bug? Where's Waldo here? Okay? And when you plug those values in, that gives you the temperature at that time. Now, that's not what the question's asking for, though. It says how fast is the temperature changing at that point. Okay? So basically, what we have here is, and it's just like I've done it here, d by dt of t, that. And what the rule, theorem 2, tells you that is, this is the gradient of t, that's your temperature, okay, at r equals 0.6 seconds, or they just do r of 0.6. Dotted with, that's the vector, dot that with your r prime at 0.6 seconds, okay? So even though they showed in the book where you're located, which is a fine thing to know, but it's sort of immaterial to your answer, because the answer is the dot product of those two. So chicken and egg, it doesn't matter which you do first. The gradient of t is what? What is the gradient of t? Do it of the original function. Grad t, mine get worse and worse, don't they? Okay. Grad t is the partial of t with respect to x times the partial of t, comma, the partial of t with respect to y. As a second. So really the first thing you do is take the derivative, the partial of t with respect to x and y. So what is the partial of t with respect to x? Partial of t with respect to x. All right, okay. Negative 3, that's negative 3/10 times 10 is negative 3 e to the negative, negative 0.3. I meant to put it on the outside. I'm running out of room, so let me try to conserve a little bit here. Negative 0.3 x squared plus y squared. Okay, so I'm going to put the 2x out here, so that would be a minus 6x. Okay, that's ugly. So let me erase that and make it a minus 6x. But you see where it came from. Minus 6x e to the that. That's the partial with respect to t. Okay? Partial t with respect to x. Partial with respect to y, guess what? Just like it, except minus 6 y e to the minus 0.3 times x squared plus y squared. Okay? So those are your components of this. So this is going to be a vector, which is minus 6. Now, I apologize, you do need to know what r at 0.6 is. Why do you need to know that? Because you need to know what your x is and your y is at that time. Okay? So, whether you actually do it this way or just do this is your x and this is your y and do it at that time. So this would be cosine of .6 minus 2 is negative 1.4, comma, sine of 1.2, right? So you do need to know those, Matt. Sorry about that. There was a reason for that, but it shows up now. What is your x? Now, just in case any of you are tempted to do it in degree mode, resist temptation. You're always in radians. Just about always in calculus, you're in radians. Don't ever slip up and put it in degrees. So if you put that in radian mode, what do you get these values to be? I could read it out. Second?
0.18.
Well, they put 176. No, 170, they say. Do you not get that? Okay. Say that again. Okay, there's a big problem here they have sine of 0.6, but it should be sine of 1.2. Which one do they really have here? What is sine of 1.2? Okay, so in your text, yeah, it should be 1.2. Okay. Again, this is the first time I've taught this class from this edition, so I hadn't noted that before. So that is 0.932. That's why you need that. So Matt, you were right. You needed to do that. Here's why, because you need to know what your x and y is. So here's what it is, 0.170, 0.932. Okay. This is your x, this is your y. That's the value you put in here. Okay? Wow. So, this one here is -6 times 0.170, because that's -6x, e to the minus 0.3 times, and you gotta, let's go on and do this once and for all, 0.170 squared plus 0.932 squared. 170 squared plus 0.932 squared equal, what do you get? 0.028, okay. And the other one's about 0.8285, something like that, huh? Okay. Okay, add those two together. I think it's still 89 what? 898? Okay. We'll just do that, okay, and be done with it, okay? That is your x component. Your y component is -6 times -6 times 0.932 e to the -0.3. I should have had you go on and multiply what that is. And that's also going to be 898. Okay. What's that? E to the -0.3 times whatever is in that parenthesis, 0.898. So go on and do that. I mean, you got this, multiply by that, do the E of that. And you can even do a -6 of that. And then you multiply 0.170 times that and multiply 0.932 times that. Okay. Those give you the numbers that are your temperature gradient at time t equal 0.6. We'll dot that with the r prime. Now we haven't done r prime yet. So let's do r prime. Oh, we sort of did, didn't we? No, we didn't. R prime. But what I'm saying is, always do the gradients, the derivatives, and everything with respect to the variable first, then plug in. You did need the others up there, but for a different reason. So what would this be? If r of t is equal to this, what's r prime of t? Negative sine of what? T minus 2, comma, 2 cosine of 2t. Got it. And let's go on and plug in the 0.6 there too. So that'd be negative sine of -1.4, right? Comma, 2 cosine of 1.2. Right? What's the question I've lost?
He was making sure something he could see it correctly, I guess.
Okay. This is the vector we got with that vector. We haven't written out what that vector is yet, but you can do it. To save yourself grief, like I say, is do e to the multiply 0.3, negative 0.3 times 0.898. Don't be the same in both to do it. And then raise e to that number, drop e to that number. Multiply that by negative 6. That gives you your base. Then multiply that by 0.170, that's your x coordinate, by 0.932, that's your y coordinate. That's that vector. This is the second vector. You dot those two, that one times this one, plus that one times this one. Whatever it turns out being, that then is the rate of change of your temperature per time. Okay? How fast the temperature is changing at that time. The dot product of these two vectors, if they scaled them right, which I assume they have, but I don't know that for sure. If they have scaled them, the dot product is going to be basically the magnitude of this times the magnitude of that times the cosine of the angle in between, which appears to me to be second quadrant type thing. Cosine there is negative.
Yeah, negative 0.76.
Is that what you get?
For the x coordinate. Well, for the first part, for the first multiplication between sine and the negative 6, 1.7.
This thing right here.
Yeah.
What does that give you?
Oh, just that thing I already multiplied.
Oh, okay, good. Okay. Times the sine? Okay. That gave you?
Negative 7, or 0.7.
6.8. Plus? One point three.
For that, I get negative 3.0. Let me make sure I didn't.
Let's say
I got negative 3.09.
3 point or 0.3?
Negative 3.1.
3.1. Okay. So this looks like this is going to be something on the order of negative 4.868. Okay. Let's see what they got. I didn't have a calculator, so I wasn't following you. Negative 3.87. Oh, yeah, 3.87. Where did I get a 4? 3.868, which is about negative 3.87 degrees Celsius per second, I think, or minute or hour or whatever it was. What was that time in? Second. Okay. So the temperature was changing for that bug at about negative 3.87 centimeters per second. Not degrees Celsius per second. Okay. Now, what does that mean? Well, it does look like it was a negative temperature gradient here, and whatever that was, it was dropping not quite as fast as global temperature, or increasing, but never mind. Okay. Had to throw that in. All right. See how it works? Messy numbers that they dealt with, but they're just numbers. Calculate them. How are we doing on time? It's what? Oh, 138. Yeah, we got plenty of time. Okay. Now, let's move on to example 5. And this also doesn't have a graph, so this one doesn't, so we'll just write on this one. Calculate, this hopefully will be a little bit better, d by dt of f of r of, you got your test too, right? Yeah. R of t when t is equal to pi halves, where f of xy, no, xyz, sorry about that. Is equal to xy plus z squared. Okay. And r of t lost it again. Cosine t, sine t, t. Okay. Don't know if you recognize it, that's our good old helix. Increasing. Could be decreasing too, but count that. Okay. T equal pi halves it be going upward. Scrolling up. All right. By our formula, what would this tell us? Derivative of a scalar function of a vector quantity, okay? This would be what? It's kind of like a chain rule. You take the del gradient of f at r of t and dot it with r prime of t. That's a vector, that's a vector. Okay. Now, things you have to do, and you've got a time t, or t is equal to pi halves. So, let's start by, as Matt was suggesting before, r of pi halves. You take the derivative before you do this, but you still have to do this at some point, so let's do it. What was that vector be? Anyone know? Cosine of pi halves? Help me. No, sine of pi halves is 1. 0. Next. 1. Next. Pi halves. Okay. This is your x, your y, your z. That's why you do that. Okay. Now, the gradient of that function, let's do what that is. Can you do that just sitting there looking at it? Why not? X, 2z. Does everybody see how he got that? Okay? Yay or nay? Yay. Okay. Yay. All right, you got it. Okay. Now, can we do r prime of t just by looking at it? There's your r. Do r prime. Negative sine t, comma, second, cosine t, comma, 1. Very good. Okay, now we plug in values. Okay. The y from up here was What's your y up there? 1, 0. I'm sorry? Pi. I love that sound of that. Okay? Dotted with, and remember here your t is pi halves. -1, comma, 0, comma, 1. Now, the dot product's the easy part, isn't it? What would that be? -1, right? Plus 0, plus pi, and what did you say, pi minus 1? Okay, I couldn't hear. Okay, pi minus 1. Seems so easy. Yep, that's what they got. Do you see how that works? Just have to keep it straight what you're doing. You're taking a derivative of a scalar function of vector of a vector. It's the gradient of the scalar function dotted with the derivative of the gradient. Okay? Yes.
I can't get it. Can you go back to the y, x, and 2z?
Do the what again?
We got y, x, and 2z.
Right here?
No.
Okay. This one here? Okay, right.
Can you get that again?
All right, okay. Okay. We're doing the gradient of this vector here. Okay? I mean, the gradient of this function here. Okay? Here's the function, this one. Now, are you asking how to do a gradient? Okay. How you do a gradient is the partial of this function with respect to the first variable. So the partial of this function with respect to x. What would that be? Take the derivative of x, which is 1, and count the others as if they're constants. So that would just give you the constant. 1 times the constant y, right? Derivative of a constant is 0. So that would just give you y. So that's where that came from. The gradient of f, the first component is the partial with respect to x. And that was the y here. Okay? The second component is the partial of this function with respect to y. And what is it? X. It's just a constant times y plus a constant. Derivative of that would be the constant here, because y, derivative of y would be 1 times the constant. So that would be x. So that's where that came from. And then the third component of that gradient is the partial of this with respect to the third variable with respect to z. These are just constants. Derivative of that is 0. Derivative of z squared is 2z. So that's where the 2z came from. Now, what are those x, y's, and z's? They are the values of this function at this value, at pi halves. T equal pi halves. Your x was 0, your y was 1. Because your t is pi halves, cosine of pi halves is 0, sine of pi halves is 1, and the pi halves is pi halves. Okay, that's your z value. So you put those values in here. The y is 1, the x is 0, and 2 times pi halves is pi. Okay. So that's your gradient of that function at that value. Okay? Dot that with the derivative of this function. Well, the derivative of cosine t is minus sine t, derivative of sine is cosine, derivative of t is 1. Now you plug in t equal pi halves. This will be a minus 1 here, a 0 here, and a 1 there. Now you dot product these two, which is this times this is -1, this times this is 0, this times this is pi, so it's minus 1 plus pi, or pi minus 1. Yeah. Okay. Yeah. Lots of steps in maneuvering, but each one of the steps is pretty straightforward. It's just getting them in the right order and putting them together correctly. After that, it's easy. Oh, okay. Dot product's the easy part. Okay. All right. Got about 6 minutes. Let's now talk about directional derivatives. We come now to one of the most important applications of the chain rule for paths. Okay. Consider a line through a point P, and the P is the value AB. Let me blow this up for now. Might be able to keep it blown up pretty much forever here. Okay. Now, what did it say again? Consider a line through a point P, AB. So here's the point P, AB. Okay, that's that one little point there. A here on X, B here on Y. That's the point AB. Point B. Okay. Now, in the direction of a unit vector U, which has components HK. Okay? Here is the unit vector U, HK. Now, what does that tell you? The square root of H squared plus K squared is equal to 1. That's what makes it a unit vector. Okay? So here's the point AB, the line through AB in the direction of that unit vector is that line right there. Okay. Now, and again, the new addition is calling this R, which to me is a fantastic choice. Oops, I can't write there. Okay. This is R of T. Okay. Now, that vector R of T is the vector R pointing to any point along that line. It's A plus TH plus B plus TK. Comma B plus TK. The X component of this is whatever your A is, plus however H is changing per unit time T. That would be that much. B comma B plus TK. And K in this case is a negative, slightly negative. TK would be down here. So R of T at any time T would be that. If T were negative, you'd be back here. T positive, you're somewhere along here. Okay? So that is your vector representation of that line. Okay? Through that point AB in the direction of the unit vector HK. All right. Now, the derivative of F at R of T. Okay? So, okay. They haven't told you what the F is, okay? But the derivative of the function F at R of T, that's what you're doing here, okay? At time T equals 0, it's called the directional derivative of F with respect to U at the point P, okay? The directional derivative. So in other words, okay, this is a contour map. The green lines are a contour map of the function F. At the point AB, you happen to be on that contour line right there. So you're wanting to know how that function here is changing as you're moving along R at T equals 0, which would have you right there. How is that function changing? Well, they don't tell you anything about these contours, whether they're increasing going that way or decreasing. You don't know, but that's what it's telling you. That's what the directional derivative is. Directional derivative d, that means derivative with respect to u, to this unit vector here, at the point AB, when you're located right there, rate of change of f along the linear path, along u, in the direction of u, through the point P at AB. That's what it's telling you. One short little shorthand here. It says derivative in the direction of u at the point AB of this function, of this field function f. I will keep on to call them fields because it's potential field basically is what you're dealing with. Okay. All right, that's kind of your definition. With a picture, here's your definition in words. All right, directional derivative. Directional derivative in the direction of a unit vector u with components hk. Note both h and k are less than or equal to 1, or absolute value of less than or equal to 1. Okay, is the limit, assuming it exists. Okay, you might say, where does the limit come in? That's your derivative part. Okay, is the limit as t approaches 0 is f of a plus th, b plus tk minus f of ab. So how is that changing as those points are getting closer and closer to each other, divided by t? So that's your differentials here, kind of. Okay, that's what your directional derivative is telling you. Where p is the point AB, u is the unit vector hk, so that's how they all fit. All right. Now they say something about, note that the partial derivatives are the directional derivatives with respect to the unit standard vectors. I don't know. Trying to find that. I don't see that in the new edition, do you? Okay. But it doesn't take much to picture that this is directional derivative in direction of any old vector v. Goodness, I don't see that anywhere here. Okay. Not necessarily a unit vector, okay, of a function at AB would be the del F dot B, okay? Now, the only thing that looks a little strange here is that before, if you're taking derivative with respect to time, that would have been an R prime. Now it's V, and maybe that's why they left it off here. They'll pick that up later. I don't know why in the old edition that was here. So let's move on from there. We're out of time. Sorry. Okay. Anyone who came in late, if you did not get your test, who was that? 2 of you? 3 of you? I think that's one for you. That's one for you. Anyone else who came in late didn't get a test? Okay, put it right there on the, yeah. Did you get a test? Oh, yeah. You did, great. Okay. Now, let me go over what you have to do, okay, on the test. We got number 1 covered, number 2 covered, number 3, number 4, number 5, I think, number 6, number 7, number 8, number 9. Don't think we got to do 10. So 1 through 9 are required, 10 is optional. Okay. Oh, the sections? Okay. I'm pretty sure 1 and 2 are from section 1. Let let me check that out before I confirm that. 14.1, I think. Yeah. Believe, think that's true. And then 14.2, pretty sure that's, let's see. No, I take that back. 14.3 is 3, 4, 3, and 4. 14.3. So I think number 1 is from 14.1, number 2 is from 14.2. 3 and 4 are from 14.3. Five I know is from 14.4. 6 is from 14.5. 7, 14.5. I swear, I think 8 is from back in 14.3. Yeah. Oh, wait. Hold off on 8. I think 8 is something that we haven't done yet. Let me see. No, 8 is from later. Implicit differentiation. Okay. So 1 through 7 you're responsible for, and 8, 9, and 10 are optional. No, wait. You've done 9. We've done that. 1 through 7 and 9 are required. 8 and 10 are optional. Okay? 9 from that last section we just did.
What was that? 14.5. So 9 is 14.5. What was 8?
8 was, that was 14.6, so we didn't get that covered. That's optional.
And what's
10, oh, I see what you're getting at. I believe that's 14.7. Yeah, 14.7.
And those are bonus points?
Those are bonus. 8 and 10 are bonus. All right, good deal. Good class, by the way.
And where will you be?
I have, okay, today I'm in my office for the rest of the day until around 5:15 or later, probably. Tomorrow I'm on the, tomorrow's Thursday. Tomorrow I'm on this campus where I've got class at 8, class at 9:30, class at 11, and class at 3:15. So from 12:15 to 3:15 I'm in the office, and after 7:45 I'm trying to get home as soon as I can. Okay, so I'm not in the office much more. Friday I'm on Birmingham campus, 7:45 to 11:45. Next week, 8 to 9:50, I'm in this room, but I'm doing a review session for a class. So you can bring stuff by or slide it under my door, okay? 265. That's my office door. Not this office room, but my office 265.
So your office is 265?
265, right. Now, but 8 to 9:50, I'm in here giving doing a proper review session. Tuesday from 8 to 9:50, I'm in here giving a test. And then periodic, the rest of my tests are all, no. Thursday afternoon, 3:15 to whenever, I'll be up here giving a test. It'll probably be done within an hour. So I'll be back in my office after that. But except for that, I'll be in the office most of the time, except when students come in to do a makeup class, a makeup test, and then I'll move to the closest classroom between here and there, between 255 and 265, the closest to 265. Look for me in any room there that's open. If you don't find me in my office, start coming up to classes, both sides of the hall, till you get to here. I'll be somewhere in that. If not, go back to my office and wait and then try it again.
Yeah, I'll be right down there, right?
265, down as far as you can go before you hit the stairwell. It's on the left.
Okay. Were you giving us our test?
Oh yeah, I was going to do that today, and a lot of people left before I got it done. So if you see your classmates, tell them they can come out. But please, folks, don't share these tests with anybody because not everybody's turned them all in. So I can't return your research papers because they periodically ask for samples of student writing. But Ashley's not here. Tony's still here? No. Okay. Cameron's not here. I'll get him his. Tariq? Matt? Jonathan? Nigel? Okay, that's test 1. Test 2, Matt. That's all she wrote.
See you in your office?
Huh? I'll be in the office from.
I'll set a camera because I'm going to the scholar board.
Okay.
I'll set a camera because I'm going to the scholar board.
Oh, I see.
If he's in there, I'm going to tell him.
Okay. Yeah, well, he's my work study student, so I'll see him. Yeah. Okay. The rest of you get your test 2s in and get the third test as soon as you can. Good deal. Enjoyed having you in class. Please do your student course evaluations. Oh man. Got this out of order. Oh man, I forgot to turn off this.